Thank you for coming. My name is Hernan, and this is Agustin. Yep. And as you can see, the name of our presentation today is Understanding the Windows SMB NTLM Authentication with NAND Vulnerability. So basically, the idea of the presentation is to describe this vulnerability in detail, to explain and demo 3 different techniques that we developed to exploit this vulnerability. We are also going to clarify some misconceptions that I think people have about this vulnerability. We are also talking about the scope, the severity, and the impact of this vulnerability, because I also think that that is not very clear. Also, I think that if you have read the advisory published by Microsoft, some of the things that are there, I don't want to say are not accurate, but not the whole history is there. And finally, we're going to pretty much make a summary of the things that we describe through the presentation, and share some things that I think, some security issues that we can be reminded of by this vulnerability, and that perhaps you can apply in the future when analyzing similar protocols like NTLM. Basically, this vulnerability is not just one vulnerability, but consists in a series of flaws in the way that Windows implemented the NTLM authentication protocol. An attacker that can exploit these flaws can access the SMB service without any kind of credentials, and once he has done that, he can gain read-write access to files, gain access to any kind of resource that is being shared using SMB, and also execute code remotely by using DCE RPC over SMB. We published this vulnerability at the beginning of this year, and we also published an advisory at that point in time, and there is a patch already for this vulnerability. So why do we think that it's worth talking about this vulnerability? Well, basically, the flaws that we found in the implementation of NTLM, that is basically the most widely used authentication protocol in the world, have been there for not only 14, actually 17 years. So this basically means that since Microsoft shipped the first version of Windows NT, and that is Windows NT 3.1, up until February of this year, the NTLM authentication protocol has been seriously flawed. So if you have been worried about attacks such as SMB relay, or also known as the SMB credential reflection attack, or pre-compute dictionary attacks against NTLM version 1, well, I think that this is basically worse than that, because the protocol implementation was flawed, allowing for other attacks that are more dangerous than those ones. And this flaw, like I said, affects all versions of Windows, from Windows NT 3.1, NT 4, 2000 XP, 7, 2008. All versions were vulnerable. Besides that, we also think that from a technical standpoint, this is kind of an interesting vulnerability, because we're not talking about something that is more common to find nowadays, like buffer overflows, integer overflows, or things like that. But this vulnerability or series of flaws has to do with issues in the pseudo-random number generator used by the implementation of NTLM, that we think is pretty interesting. It's not something that you find all the time. And also other implementation issues that we found in the protocol that allow for side-channel attacks that can result in, for example, replay attacks, and also an attack that also we think that by itself is very interesting, that is the possibility of predicting challenges. And we're going to see what all this means. So in order to understand the flaws, you need to understand how NTLM works. NTLM is basically a protocol that belongs to a family of protocols that are called channel response authentication protocols, or perhaps cryptographic channel response authentication protocols. So what is a channel response authentication protocol? Well, the idea is pretty simple. You have a client that wants to authenticate against a server. The client wants to prove to the server that he is who he says he is. Both entities, the client and the server, share a secret, for example, a password. And the client wants to prove to the server that he knows the secret, in this case, for example, the password, but without actually sending the password. Otherwise, we will be talking about something like the telnet service where you are sending the password. And we're trying to avoid that. We're trying to avoid revealing the password, because we are doing all this over a channel that is not encrypted at all. So how you do that? The solution proposed by the channel response protocol to this problem is to, every time that the client wants to authenticate against the server initiates an authentication attempt against the server generates what is called a challenge. The client receives that challenge and performs some kind of computation, applies a function or an algorithm to that challenge and to the secret. Takes the result of that calculation, sends that result to the server applies the same function or algorithm to both the secret and the challenge, and if the results match, that means that the client knew the secret. And the secret, that in this case could be the password, was actually never sent to the server. One thing that is very important about this whole scheme is that the challenge, that is usually a number, has to have certain properties. If the challenge does not have these properties, the whole protocol falls apart. The security of the protocol breaks. Some of these properties that the challenge needs to have, the challenge is usually a number, and this number needs to be non-predictable. For example, if the challenges are 1, 2, 3, then 4 and 5, that's predictable because you know that the next challenge is the previous one plus 1, so that's not good. Also, the challenge has to be a unique number. If you, for example, issue the numbers 1, 2, 20, 19, 2 again, you don't want that because that also breaks the protocol. So those are very important things that the protocol have to adhere to. If these properties are not met by the challenge, that is usually called a nonce, hence the name of the vulnerability, some attacks can happen. For example, if the server generates duplicate challenges, that is, generates the same challenge over and over again in a short period of time, what an attacker can do is just, if the attacker is able to eavesdrop the communications between the client and the server, he can just look at the traffic without knowing nothing, just look at the traffic and create a dictionary of challenges sent by the server and responses sent by the client. So he has like a dictionary where he has a column with nonces or challenges and a column with the responses. Just by having that, since the attacker knows that the server is going to issue duplicate challenges, what the attacker does is connect over and over again against the server until the server responds with a challenge that the attacker has seen before and that he has in his dictionary. So for example, in this case, the server issued the challenge, the number 2, the client issued the response 4, the attacker grabs that and saves that, and then the attacker starts performing authentication attempts against and again and again against the server until the server returns again the challenge 2, and at that point he replays the response that he has previously and can gain access. So that's the problem that can happen if the server generates duplicate challenges. The other thing is, for example, if the challenge is predictable, let's say that the attacker can predict when the server, at which point in time the server is going to generate certain challenge, that is a number. So by knowing that, the attacker actually uses the client, forces somehow a connection from the client to the attacker to obtain the corresponding response for that challenge. So now the final step is the same as before, but this time the attacker connects at the exact time that he knows the server is going to generate the challenge that he predicted, and at that point sends back the response that he got from the client and gains access. If we take a look at NTLM, it works exactly like this generic example. Here you can see a typical NTLM version 1 authentication communication. For example, when the client wants to communicate with the server, the client sends an SMB negotiated protocol request packet that initiates the authentication attempt. The server responds with the challenge that in the case of NTLM is an 8-byte long challenge or nonce. The client sends back a response. We don't care for our purposes how this response is actually calculated, but as you can see, it includes the username, the domain, and the hashes of the password. That would be the secret in this case. The server performs the same calculation that the client did to send back the response, since he also knows the hashes of the password of the user. And if everything matches, allows or disallows access to the client. So here you can see a typical example of an NTLM version 1 authentication process, basically so you can actually see what goes over the wire. You can see the challenge in red over there sent by the server, and in the bottom of the slide you can see the response sent back by the client. If we take a look at NTLM version 2, it's practically the same. The only thing that changes is how the client calculates the response that is sent back to the server. But pretty much it works the same way. Again, a typical example of what you will see over the wire, the challenge generated by the server and the response sent back by the client. So, since this is a challenge response authentication protocol, the nonces generated by the server, need to have the properties that I said before when I was talking about the generic example of a challenge response protocol. It needs to be non-predictable and needs to be unique. Otherwise, we have a problem. So basically the thing is, if you connect over and over again against a Windows server, you should expect that the server will return a nonce that is non-predictable and always a different number. Well, the first flaw that we found actually was that the server was returning repeated challenges. And that's a big problem because that is breaking the security of the protocol. And not only that, it was not returning duplicate challenges, but it was doing so in a very short period of time. Because it's not the same thing if you get a duplicate once a year, for example. But if you get a duplicate once every 2 seconds, for example, that's a bigger problem because you can do all the attacks that I talk about when talking about the generalities of a channel response authentication protocol. So basically, Agustin here is going to show you some plots that we did that are trying to show you how often, how many, and how are the nonces generated by a Windows server that is vulnerable to this vulnerability.
Hi. So we wanted to have a visual idea of how often the server was generating duplicate challenges. So we perform multiple connections to the server and save all the challenges. So we saved a sample of 64K samples, and we try to plot them. So we counted the number of occurrences of each challenge and plotted it in a graph. So for example, this is the first 4K sections of the sample where there are only unique challenges, so they are plotted at number 1. And if the challenges are duplicated, they will plot at number 2, for example. This is the first 8K section of the sample where we can see duplicates. And here, this is the first 16K of the sample where we start observing 3 times issued challenges. And this, for example, is the whole sample, where we can see how the duplicates line is getting thicker, mimicking the unique challenges, for example. So going back to the 16K sample, we can see some kind of small pattern duplication. There are 4 little dashes there that I want to know what's happening there, so I have to visualize each duplication in a separate way. So we plotted that in a different way. We assign to each duplication of the challenge a unique ID, and we plotted the pairs. So if we imagine the duplicate ID as a progression, or we can see it as a curve, we can see different regions and we can see different patterns. For example, we have a pattern A, which is found in steep regions of the curve, meaning that within a short time frame, a lot of challenges that are going to be issued are going to be duplicated later. And we can see a pattern B in smooth regions of the curve, meaning that within a time frame, the issued challenges are not going to be duplicated later. And we can also see a pattern C, which is found below the curve of IDs, which mimics a pattern A, and that means that within a short time frame, a lot of duplicate challenges were issued in the same way as a pattern A. So for us, this is enough information to carry some attacks.
So basically,
these are different sections of the 64K sample in chunks of 16K, and we can see all those patterns in this plot.
basically, I know that perhaps the graphs are kind of difficult to understand, not because they are very complex, but because you need to kind of have some time to understand them. But the thing is that you are seeing a lot of points everywhere. That means that within a very short period of time, the server is generating a lot of the same challenges. And like I said, this is very, very bad. That's the general idea for that. So just by taking into account that we know that the server is generating a lot of duplicates, what can we do with that? How can we exploit the fact that the server is generating within a very short period of time the same nonces over and over again? Well, the first two attacks that we're going to talk about are going to exploit that. Those are the passive replay attacks and the active collection of duplicate challenges. The third one, the active prediction of challenges, actually is a different flaw that we found in the same code and has nothing to do with the fact that the server is generating duplicate challenges. But we're going to talk about that later. Agustin is going to explain how that all works. So let's start with the passive replay attack. Basically, the attack is super simple. It's like I said before. You have a client that is, or you have a network where you have client and servers that are authenticating, performing NTLM authentication between themselves. And you have an attacker that can eavesdrop the traffic between them. What the attacker has to do is just listen to the traffic without doing nothing, just listen to the traffic that goes by from client to server and generates a dictionary that has the nonces generated by the server and the response, that is all that information that you see there in the table, that was sent back by the client to authenticate against the server. Once you have that, the only thing the attacker has to do now is, since he knows the server is going to generate a lot of duplicate challenges, so it is very likely that the challenges that he has in his table or dictionary are going to be generated again by the server, the attacker starts connecting over and over again against the server until the server returns one of the nonces that he observed previously by eavesdropping the traffic between the two. When he finds that situation, the attacker just gets from his dictionary the response that he got just by eavesdropping the traffic and sends back that response. And that alone is enough for the attacker to actually gain access to the SMB server as the user from which he obtained the response and the nonce. So it's very simple and it's kind of scary because someone can actually do this by doing nothing, just listening to your traffic. It's not exactly the same, but I would say it's equivalent to someone just sniffing a telnet session. One thing that you need to understand about NTLM that is relevant to this particular attack and also to some extent to the other attacks that we're going to show you is that there is more than one way or mode to perform NTLM authentication. And I'm not talking about NTLM version 1 or version 2. I'm talking about modes where the difference is given by the kind of packets that are exchanged to actually perform the NTLM authentication. The first slides that I show you where I had the examples of how NTLM version 1 and NTLM version 2 work, that can be called NTLM in plain mode or plain NTLM, regardless the version that you're using of NTLM. And there's another mode that is called by some people SMB extended security or NTLM SSP. And the package, as you can see in this slide, is slightly different from the other packets that I showed you before. The basic idea is if you see two machines actually using NTLM SSP to perform authentications, the code that generates the nonces or the challenges is some other code that is different from the code that where we found these flaws. So if you're trying to perform a passive replay attack against two machines that are using NTLM SSP, you won't be able to do so because the server is not going to generate duplicate challenges. Which mode is actually going to be used between two Windows machines is determined by a bit in a field that is called flags2 in the SMB header of the SMB negotiated protocol request packet. That is the first packet that is sent from the client to the server when the client wants to authenticate against the server. The thing about this is that for some time now, I think that starting with Windows 2000, Windows machines use between them the NTLM SSP mode. However, this does not mean that passive replay attacks are not possible, because like I said, the client can say to the server, hey server, I want to use the plain mode. And for example, SMB client with certain configuration options, and OS 10, for example, 10.3 and other operating systems, and for example, Windows NT, during the whole time where Windows NT was actually in use, Windows NT was never using NTLM SSP. So even nowadays, and a lot in the past, passive replay attacks were totally possible. And actually, in order to understand if your network actually is vulnerable to passive replay attacks, you have to understand all the clients that you have in your network. Because like I said, the mode that is going to be used can be determined by the client, and that determines if these attacks are possible or not. And actually, the fact that nowadays, Windows machines between them do not use NTLM SSP, that will work to our advantage to perform one more advanced attack, that is the prediction attack that we're going to show you next. We're going to explain you next why. Basically, it's because since the code that is vulnerable is not triggered that often, that helps us because the internal state of the PRNG that is used by that code is not modified so much, so that will allow us to actually predict the internal state of the PRNG. But don't worry about understanding that, because you're going to see it in much more detail with Agustin later. When we're talking about the other attacks, we call the other attacks active attacks. This is the attack that I'm going to show you next. The fact about these modes and NTLM SSP and the play mode doesn't matter, because like I said, the client can tell the server, use the mode that I want. And as an attacker, we can say to the server, use the mode that I want that I know is vulnerable. And that attack also includes some part of the attack where the client has to communicate with the attacker. And in that case, the attacker can also say to the server, hey, I want to use the vulnerable mode. So for the active attacks, we call them active because we are forcing the client to do something for us. In the passive replay attack, we just listen to the network traffic. That's why we call the attack passive. So for the active attack, you don't care about all these things with NTLM SSP. So pretty much, it's always exploitable. That's the bottom line. One thing that is interesting about NTLM version 2 is that actually to prevent pre-compute dictionary attacks, NTLM version 2 includes some entropy generated by the client. And it also includes, if you can see at the slide, there's a field that is hashed in the response sent from the client to the server, that the field is a timestamp. That is hashed with some other information. The thing is that the server could actually use that timestamp to determine if a response that he's receiving is old or was just created by a valid client. Well, the thing is that Windows does not check this timestamp at all. So you can create a dictionary today, and that same dictionary will be valid in 2 years, because Windows is not checking that the timestamp of the response was generated within a short period of time when he's receiving the response. This is something that has been happening since Windows NT4, I think. I don't know if later versions of Windows actually, for example, Vista or something like that, have fixed this issue, but we did a lot of tests with XP-SP3. It does not check nothing like this. And also the people of the Samba team also have published things about this, saying that Windows NT does not check this. Even if this is the case, with Windows NTLM version 1, you don't have any kind of timestamp or nothing, so you can exploit and reuse and replay the responses all the time. They will never expire. You can use them forever as if you had the password. So the next attack is called active collection of duplicate challenges. The idea is the same. We want to build a dictionary where you have the nonces and the corresponding responses. But in this case, instead of getting the responses by just looking at the network traffic, you're going to force the client to give you the responses. So basically, the first thing that you do is you connect over and over again to the victim. It can be a workstation where some user is doing something. And you connect over and over again, and you create the first column of the dictionary, or a list of nonces returned by the server. Once you have that, you want to obtain the corresponding responses for those nonces. So you actually have to force the client somehow to give you those responses. The most, I would say, common way to do this, and very well known, is, for example, send an email with a link to a website, or with embedded HTML with some multiple image tags that will, when rendered, will make a connection to the attacker that is running a custom SMB server. So you send an email with all these image tags, and when the user receives this email, goes to a web page, someplace on the internet. If they are using Internet Explorer, for example, that will cause the workstation to start performing authentication attempts against the attacker. At that point, what the attacker wants to do is get the responses for the nonces that he has. So he sends back the nonces that he got in the previous step to the client. The client will give the attacker the response for that nonce, and the attacker in this way will do this over and over again for all the nonces that he has in his dictionary, and will complete the dictionary with all the nonces and the responses. Once the attacker has the dictionary with all the nonces and the responses, again, the attacker knows, because of all the things we research and we show you with the graphs, we know that the server or the victim will generate, for sure, one of the nonces that we have in our dictionary. So the only thing that we do is we start connecting over and over again against the workstation until the workstation or victim sends back one of the nonces or challenges that we have in our dictionary. When that happens, we're going to send back the response that we obtained from the client or the victim, and we're going to be able to gain access to that machine. All these things that I'm mentioning can be done in, I don't know, seconds, like 1 minute, something like that. So it's pretty quick. I mean, also one thing that we observe when doing all these attacks is that if you go to some machine and you get from that server a lot of challenges, then you can go to other server and also request a lot of challenges from this other server, and you're going to obtain the same nonces that the other server gave you. So basically this means that two servers will generate duplicate challenges between themselves. So you can do the attack to one machine and then move to another machine, and you can use the same dictionary with other machine. So this is kind of interesting because you can attack one workstation, for example, in an internal network, something like that, and then you can go to some other machine where the user you're attacking has an account, or if you're in a domain, a machine where the user can actually connect to because he has permissions to do so, and use the same dictionary over and over again. It's like having the password. It's almost the same thing. And not only that, we also realize that you can turn off the machine, turn it on again, and the same nonces are going to be generated by all the servers. It's kind of that bad. So that is good for the attack because you can reuse all the dictionary that you have, that you will see in the demo that you can obtain that dictionary in, I don't know, 2 minutes, and then you can reuse that as if you have the password over and over again, and with different machines, with the same machines all the time. And now, Agustin is going to explain to you how the third attack, that is a different vulnerability or a different flaw that we publish inside this vulnerability report, that actually exploits the fact that we can predict the challenges or nonces that the server is going to generate. In order to do that, you need to understand the whole mechanism that the server uses to create these nonces. And Agustin is going to explain as better as we can that, because it's kind of complex, so bear with us.
Hi again. Well, once a server receives an authentication request, it will call the function getEncryption key to generate a challenge or an encryption key as it is described in protocols. So I will explain the getEncryption key function. First, well, the getEncryption key function is inside the srb.sys module. And the first thing it will do is retrieve the current system time using kernel query system time and create a seed. We'll create a seed with a part of that time and also using a counter, which is called encryption key count. Then, once the seed is created, we'll call the RTL random function, which is a PRNG. And with that, we'll create a challenge and return the challenge to its caller as a function. So this is the get encryption pseudocode that we arrived after disassembling the get encryption key function. The first thing we see is how it calls the query system time function. With the low part of the return value current time, we'll add a counter and we'll update that counter. And we'll create a seed using that formula. We'll only use the low part of the current time and only the middle 16 bits. And we'll add and subtract a number. And once the seed is created, we'll call the RTL random function 3 times in a row. The first time, we'll use the created seed, and the second and the first time, we'll use some kind of feedback that the RTL random function returns also. With the 3 numbers returned by RTL random function, based on the third one, we'll modify the first and the second number, and we'll concatenate the results and return a challenge. That will be the challenge. So we know that the get encryption key function gets entropy from the current system time and also from the counter. We'll create that seed, we'll call RTL random, and we'll return a challenge. So if we know the internal state of RTL random function and the current system time and also the value of the encryption key count, we can calculate all the numbers returned by RTL random function, and we can predict the challenge to be issued in the future. So I will explain the RTL random function in detail. Well, first, the RTL random function is a PRNG, which appears to be a Maclaurin-Marsaglia system that I will explain later, which uses 2 LCGs that I will explain later. So first, we'll create numbers using 2 LCGs as an M&M system. We'll fetch a value from an internal vector. The internal vector, it is related to the M&M system. We'll store a value into that vector, and we'll return the previously fetched value from the vector and a context to its caller. So I said that an M&M system uses 2 LCGs. LCGs are linear congruence generators. These functions are good for statistical randomness and for simulation, but it's not suitable for cryptographic purposes because it generates a predictable sequence of numbers. Well, M&M is the form of the RTL function. That's the algorithm for creating the sequence of number. It was proposed around 1956. And the authors wanted to improve the randomness in statistical means of the LCGs. In the paper that they are proposing that, they are also proposing using a table of known random numbers because they need the properties of random numbers, but they are not dealing with prediction or predictable sequence in the future. They are dealing with long periods of random numbers. So the basic algorithm is first create 2 numbers using the LCGs, construct an index to use it in the internal vector, fetch a value that I will call set, and store a value, and we'll return the previously fetched value. Well, I have like a little demo of what's happening inside there. We have the vector with n size length, which is initialized. First, we'll call the first LCG, then the second LCG. Based on the output of the second LCG, we'll create an index to use it to address values in the table. We'll fetch a value at the index created, and we'll store a new value, which was created with the first LCG, and return the previously fetched value. So again, a pseudocode of the RTL random, in this case, that we disassemble. We have, well, the context that it needs for the LCGs. First, we can see the formula of the LCG. It doesn't matter right now what's happening right there, but that's a formula of an LCG. That's the second LCG, so we have 2 numbers created. The second number will be returned as a context. Then an index will be created, and that index will be used first to fetch a value, and then to store a value. And we'll return the previously fetched value, and also the context. So we know that RTL random is an M&M system, so we can define two operations. A fetch operation that is dependent on the value of the table and also the seed, and a store, which is only dependent on the seed, but is independent of the values of the table. So we're trying to know what's happening between the different factors. First, what happens with get encryption key count value, if we can predict it, what happens when calling RTL random multiple times, if it changes the internal state of the vector, and also the return value of the query system time. So the encryption key count value is always initialized at 0 at system boot time. It is only updated by the get encryption key function, but as Hernan previously said, it is not usually called. So we can predict that that counter will be 0 if we start an attack. Also, calls to RTL random. Calls to RTL random may change the internal state of the vector, but that's not an issue because we can know if that happened, so we could relaunch the attack again. So the consequences of RTL random can be circumvented. And finally, what will be the time when the get encryption function is called? Well, we know that based on the plot, that could be the same among consecutive packets. Only the middle 16-bit, probably the most volatile part of that value, is used. But we also found that the current system time of the server is sent to the attacker during the SMB negotiation. So the current system time can be predicted or known by the attacker. So knowing those factors, we built an attack. We designed an attack in 4 steps. First, to set that internal vector of the RTL random in the server to a known state, then calculate all the possible challenges that can be generated by that internal state, collect the possible responses, forcing a victim to respond to all those challenges, and then connect and use a valid response because the server will send a pre-calculated challenge. So the first step, we will request authentication as an attacker to the victim. The victim, once the authentication is requested, will call the get encryption function and will call the RTL random function 3 times and will update its internal vector. So, and will return a challenge to the attacker and also the timestamp in the packets. So what the attacker can do is simulate the store behavior of the M&M and then, well, loop to A until all the simulated vector is complete. In this way, we have a simulated state of the server. So once we have that internal state, we can go to the next step on calculate all the possible challenges that can be generated with that internal state. So the simplest way is to get the combination of all those values, but we can also try to guess which values are going to be issued also, but the simplest way is to combine all the values. Then, how to collect all the responses for those challenges? Well, we could send an email to a victim with, for example, an HTML with image tags, and the victim will connect to the custom SMB server, and the attacker will send all the challenges pre-calculated using that internal vector, and the victim will send back the responses for all those challenges. And then the final step is to connect to the victim and wait for one of those predicted challenges in step 2, and respond with an informed response, a valid response, to the victim, and the victim will authenticate the attacker.
All right. I know that's like a lot of information, but the basic idea is that based on the fact that the server, based on the fact of how the function that is generating the challenges work and the choice of the PRNG the function is using, and also because the server is basically leaking the seed, that is the current system time, to the attacker, we can pretty much simulate and do the same calculations that the server does, and we will basically replicate the internal state of the PRNG in our machine. So basically, you have a remote machine, and we have our local machine, and we are going to know at any point in time what is the internal state of the PRNG used by NTLM in the remote machine when we want. So basically, that can be used to predict all the pseudo-random numbers that the server is going to generate. And that allows us to do the prediction attack. The prediction attack is basically saying, hey, I know when you're going to predict this certain challenge, just this one, and I'm going to tell the client, hey, give me the corresponding response for this nonce or challenge, and I know that I can use that to authenticate against that server or any other server. So basically, you are optimizing the attack and reducing the number of connections that you need from the client. And it's also, I think, once you have the time to understand everything, it's quite interesting in on itself from a technical standpoint. At least I believe that. So some very quick clarifications that we want to make about the vulnerability is that because of the way that we are actually getting the responses that we need from the victim or the victim in this case, some people think that this is some kind of SMB relay or SMB credential reflection attack, but it has nothing to do with that. It's actually, I would say, worse than that because these flaws are breaking like the rules the protocol has to comply with. That is that the nonce has to have certain properties. So it's kind of fundamental. It's like this is the thing that cannot be failing in this protocol, and it was failing. And also the patch that was recently published by Microsoft that fixes the one case of SMB relay or SMB credential reflection where you now, after you apply the patch, can exploit the same machine you are doing the attack against. Well, this doesn't affect this attack because this is a different attack. In an SMB relay attack, you are making a victim connect to you, and then you are relaying the connection. You are keeping the original connection open. In this case, we don't do that. We just connect to the client, disconnect. Make the client connect to us, disconnect. And then we have the dictionary. Once we have the dictionary built, we can use that whenever we want. So we don't need to maintain a session, and this is one of the reasons why this patch does not address this vulnerability. It also didn't, the patch wasn't trying to address this at all, but some people tend to confuse that. That's why we're mentioning it here. And also, like I said, that passive replay attacks are possible. I try to explain as better as I can all the things about NTLM, SSP, and how it is used by default nowadays. But like I said, depending on the clients you have on your network, passive replay attacks could be possible. And that's, I would say, one of the most interesting attacks, because how do you go about detecting that? I don't know, because you have to have some kind of IDS that knows what an attacker will look like when attempting the attack. Remember that the attack is just listening to traffic and then just connecting to a server and doing something that over the wire is the same thing that the valid client would do to gain access to a server. So one thing that we wanted to talk about, the scope, severity, and impact of this vulnerability, is that when Microsoft published their advisory for this vulnerability, they call this vulnerability an elevation of privilege vulnerability, and also said that this vulnerability was important. This is something we discussed with Microsoft. We respect their opinion, but we think that is a critical vulnerability, not actually only an important one, because the protocol is failing badly, in my opinion. And also, it's not an elevation of privilege. I mean, you can execute code, and we're going to show you how. It's not something. It's like a something that you would expect this could be used for. It's not something that we are doing because it's kind of crazy. It's kind of the same thing that SMB Relay does, or that PSExec from SysInternals has been doing for a long time. That is just using DCE, RPC over SMB to create a service and execute code that way. We also think, we think that the importance of the vulnerability is given because it's from, I mean, as someone that is looking for bugs all the time and is using Windows machines all the time, it's kind of incredible that since 93, I think, up until 2010, it's incredible to know that these flaws have been present in Windows. Because if you finally understand the vulnerability, it's like all the authentication attempts that you were doing were not secure at all. And that has a very big impact in everything that you do. And but the slide says that it's a 14-year-old vulnerability because actually before coming here, we were able to track down a version of Windows NT 3.1 and 3.51, and then we checked that those versions were also vulnerable. So actually, the vulnerability has been present in Windows for 17 years. Also, if you understand the vulnerability, I mean, if you were to check for this kind of, if you want to assess the security of a child response protocol, these would be the things that you will go and look for. Because the thing that cannot happen is that the challenge or the nonce should not repeat. So it's also very interesting to know that actually this was happening. And I'm not trying to bash anyone with this because no one is perfect and no one can find all the vulnerabilities. Just from, I don't know, from a historical point of view, it's just amazing that we just found these issues. And also, like I said, the passive replay attacks, I think, are very interesting, which also, I think, makes the vulnerability more severe, I think, because just by doing nothing, you can gain access. Also, well, if you have Windows NT servers, I know they are like very, very old, but I know companies that still use them for some reason. In those cases, there's no patch because it's not supported anymore because it's very old. So if for some reason you are still using Windows NT, you have to actually verify what function these machines are actually doing inside your network. If you're doing some critical function, don't use them anymore because you can't rely anymore in the authentication method that everyone is using to gain access to the machine. So you can't use them anymore. Also, if you have appliances, for example, that have Windows versions that are not updated or old Windows versions that will not have the patch that Microsoft already released, they are also vulnerable. All these versions, or all these appliances and all versions of Windows will be vulnerable to this vulnerability. And what is, I don't want to say special, but what is different in this case is that this is not like a buffer overflow or something where you are executing code in the stack or in the heap or something like that. Because for those vulnerabilities, even if you don't have a specific patch for that vulnerability, you can have some kind of generic anti-exploitation tool, something like that, installed in the machine to prevent generically all buffer overflows from executing code in the heap or in the stack. Or if you have an IDS that is looking for certain signatures of an exploit, you can also check for that, even if the machine is not patched. But in this case, since what is failing is the authentication itself, how do you check that? Because, like I said, an attack would look like someone just trying to authenticate against the server. So I don't know of any IDS systems that actually are looking for this kind of bugs, because they will actually need to keep a lot of state of the packets that flow through a network to understand that somebody is actually doing this attack. So this is also something that even nowadays, when you have a patch, you need to, I think, have into account to know that everything is secure. Also about this vulnerability being an elevation of privilege, we don't agree with that. First, because we don't know what is an unauthenticated elevation of privilege vulnerability. Because, I mean, elevation of privilege is when you have some privilege and then you gain more privilege. And if you have no privilege and then you gain privilege, that's not an elevation of privilege. Because that's like saying that when you find a remotely exploitable buffer overflow, that's an unauthenticated elevation of privilege. I don't think that's the case, because that's how it works. You don't have any access, you exploit the buffer overflow, and you gain access. Yes, you were unauthenticated before, but that is not an elevation of privilege. And also, the advisory says that this can be used to upload and download files and access SMB resources, and that is true, but what the advisory does not say is that it also can be used to execute code. And if you take a look at the advisories for the SMB credential reflection vulnerability, in their website, Microsoft itself says this is a remote code execution vulnerability when they're talking about SMB relay or SMB credential reflection. And this vulnerability to execute code needs to have the same context and has the user that you are attacking needs to have the same privileges that the user that you're attacking when you're doing SMB relay has to have. So if that vulnerability is considered a remote code execution vulnerability, this should be considered a remote code execution vulnerability as well. So that's why we don't agree. And we're going to show you that we can execute code. So before going into the conclusions, we're going to try to do some demos to see. Let's pray. I hope that nothing fails. All right. So the first thing that we're going to demo is the passive replay attack. We're not going to demo because you need time just to sit down and listen to the traffic. So we don't have that time. So the attack that we are going to demo is first what we call the active collection of duplicate challenges. So basically, we have a virtual machine with a SP3. And we're going to try to, that is vulnerable to this vulnerability, obviously. And we're going to do the attack against that machine. And we have to wait for it to boot. So the first thing that we're going to do is, like I said when I tried to explain this attack, is we're going to get a number of nonces from the server to have just a list of nonces generated by the server. And we're going to grab around 8,000. And this is just because the number was calculated using heuristics. But you can actually improve that. There's a lot of things that you can do to actually improve all the attacks that we're going to show you, but you need to spend more time. And after the patch was released, we just stopped researching about this. Correct. All right, so this is basically, satisfied DAPS 0?
No, lo voy a guardar, pero voy a mostrar los duplicados.
No, let's show the duplicates first. Okay, we're going to make a change. First, we're going to show you how much time you have to wait until the server generates a duplicate. So we're going to run Java program that we did that basically connects to the server, gets nonces or challenges from the server while trying to perform NTLM authentication, and we're going to see how much time you have to wait for the server to generate the duplicate. And this machine is very slow. No, but I think that the VMware server was booting. Well, that took like 2 seconds. And then you see another duplicate, another. Every time you hear a beep, it's a duplicate. The server is generating a duplicate. So as you can see, the plots that we did were true. There are a lot of duplicates, and within a very short period of time. So now what we're going to show you is the active collection, the active collection of duplicate challenges. So we're going to run this other program that basically is gathering nonces from the server, just to have a list of nonces. After we have that, we are going to force the client to connect to us and give us the responses that we need for those nonces to build the dictionary.
We can also reboot the machine, for example.
Pues. No, tiene que firmar.
Okay.
Tiene que firmar las cosas con Internet Explorer. Now we're going to simulate, I don't know, let's say that we send an email or somehow we made the victim connect to our website. So basically, we're going to simulate the victim connecting to a custom SMB server that we wrote, that basically for every connection attempt, authentication attempt that it gets using NTLM, will send back the responses or nonces that we got in the previous step and get from the client the corresponding responses that we need to create the dictionary. So basically, we have like a common web page with 2 iframes where you can see that you can fool the user like with a game of lemmings or whatever, and in the background, the code that we're sending is actually connecting to our custom SMB server. That's it. Now go to the customs. Yes, all right. So basically, it took us like 2 seconds. Now we have the dictionary. That was it. It was not like a lengthy process. edit the file that has all the, I think it's /temp/challenges. No, /temp/save2.log. So this is a dictionary. The first line is the nonce that we send to the client, and we made the client give us the response, and all the other information is the NTLM version 2 response in this case. So basically what we're going to do now is we're going to reboot the virtual machine altogether to prove that you can use that against different machines, because by rebooting the machine, we're basically erasing the internal state of the PRNG. It's like having the dictionary and coming back, I don't know, 1 year later to the same machine and trying to do the attack with that information that we grabbed 1 year ago. And we're going to show you that after rebooting, the server is going to generate the same nonces that we obtained some time ago. This is also one thing that makes the attack, in our opinion, a good attack, because you can spend, I don't know, 2 seconds to create a dictionary, and then you can come back whenever you want and just use the dictionary to gain access to the machine over and over and over again. So the exploit that we're going to show is basically, like I said, it's going to use DCE RPC over SMB. It will create a service on the remote machine, upload the file, start that file, that is an executable file, as a service, and that will basically connect back to us using the code that we use to grab a shell from the Windows machine. Now we have to wait. How much time do we have? 20 minutes? All right. Okay. So now this is like attacking a different machine or coming back to the same machine 2 days after we did the first stage of the attack, that is creating a dictionary. So we are going to run the attack. No, but it was not correct. Did you log in? That's it. So basically what that part of the exploit did is start connecting over and over again against the server until the server returned one of the nonces that we had in our dictionary. At that point, the exploit sent back the response we got from the client. We gain access. Since this was a user with administrator privileges, we were able to start a new service that was actually our code, and that code connected back to us and gave us a shell. And that's it. So exploiting this vulnerability takes you 20 seconds, I don't know. And then, for example, we can leave and try again. That's it, it worked. That means that the server generated another duplicate challenge that we have in our dictionary. And you can do this like forever. You can reboot the machine again, even go to some other machine and try the same thing, and that machine will generate a duplicate challenge also.
Well, let's go with the prediction.
You want to ask something?
In all fairness, it looks like you have the firewall turned off.
And of course, you have to have SMB open, because this is exploiting a flaw in SMB. So
you remove a couple layers of defense.
No, but that's like saying, okay, I put the machine in the bottom of the river, it's safe. Now, what we are exploiting is a flaw that is present in a service that you need to use. If you are in a network, in an internal network, and you are sharing files among the company, it's very likely they're going to have the SMB service run. Of course, if you shut down everything and you don't provide that service, if you cannot reach service, you cannot exploit any kind of vulnerability in that service. But that's something that happens all the time. It's not something that we are removing layers. Where all vulnerabilities exploit a problem in a service that you are using. If you are not using the service, so you cannot exploit anything. Does that answer your question? You're not happy with the answer? But let's say that you have a flaw in SMB that is a remote buffer overflow. Just because you have the firewall app, that means that no one can exploit that? No, because if you actually want to use SMB, that everybody uses that because it's like the most common way to share files between Windows machines, also to access the registry, to do administration, to everything. You will need that service, and you can't just shut the service down.
Here you have the ability to execute code remotely. That's
if you are an administrator, you can execute code, as I said that. And it's also the same thing with the SMB relay attack, with also known as the SMB credential reflection attack. It's also the same case. So that's a given. Yes, that's something that the user needs to have. Anyway, if you cannot execute code, you can still access the same files the user can access. And for example, you can download internal documents, I don't know, write things. If they have a share, you can actually write an executable file that's something that just hope for the user to click. Or you can download a file that has a .lnk extension and exploit some other flaw and things like that. So there's always a possibility to do something to exploit this vulnerability. Yes, there are certain things that have to happen, but these are things that are very well known and that pretty much all the attacks have into account and say that they need to actually execute code. But there are many ways to exploit the vulnerability. Basically, you're bypassing the authentication. So you can do whatever the user that you're exploiting can do. And that is bad. If it's an administrator, you can execute code right away. If it is not, you can access their files, modify their files, other things. Is that okay or no?
By the time you got it on a web page, you probably have everything you needed in the first place.
All right. We can talk about it later.
Oh, so let's go.
So the other attack is the prediction attack. Basically, what we're doing here is we are trying to set the state of the PRNG on the vulnerable server to a state that we know. So basically, that is mimicking the memory of the remote machine. So we are simulating what the RTL random function does there, and we have the same thing that that machine has in their memory in our local machine. That is the internal state of the PRNG. Based on that, we can predict all the challenges that that machine is going to generate, because they know, again, the internal state of the PRNG. So now what he's going to do is, after we created a list of all the challenges that that machine could generate in the future, he's going to make one connection attempt to that machine, trying to perform NTLM authentication. And that machine will return a nonce. We can see in Wireshark the value of the nonce generated by the server. If we are able to expand that window. There you go. So the nonce is referred to as the encryption key by the code itself that is vulnerable, by Wireshark, and by some other specification documents. It's not an encryption key, it's a nonce, but they refer to that number as an encryption key. Just saying that because it is not an encryption key. So basically, this is the file that we generated by predicting the remote state of the PRNG. And basically, were you able to see what he did or no? Yeah? So basically, he grabbed the number that the machine, we made a connection, the machine returned a challenge. And we grabbed that challenge and looked for that challenge in the list of challenges that we predicted the machine was going to generate. And we found it. So basically, the attack worked. We can predict the pseudo-random numbers, or the challenges, actually, that the machine is going to generate. And we can use that to do the same kind of attack that we did with the first attack where we executed code. So does anyone else agree with what he was saying, or is just him? Yeah, go ahead. Yes, the original advisory already had all the exploit code. It was not executing code, it was just writing a file in some directory. And this is rewrite done in Java, and yes, we are going to provide that. Yeah, on the internet. No, no, sorry about that. I don't know. I put some message in some mailing list, or you can give me your email, I can send you the link when it's available. Yes?
The technique of using an email to force the victim to do SMB
Yes. Most likely, this will be exploited in your internal network, not over the internet. The same thing happened with the SMB relay or SMB credential reflection, but yes, that's the most likely scenario. That's correct. Yes?
You said the challenges were the same on computers starting. So are they the same on every single computer, or does that change with different domains?
Almost. I mean, actually, to try to explain that, we need to explain a lot of things that we have to explain how we kind of have to do like a cryptanalysis of the whole Maglajna-Marsaglia system, and we're kind of done like half the work that is needed, and we can tell you a lot of things. Like, for example, some of these things are in the conclusions. One thing is that the function, the seed used by the Maglajna-Marsaglia system is reseed every time that you make the connection, and also you can add the fact that that's bad, because usually the code is using the same seed more than once, because they are using the current system time, and when they use the current system time, they actually, for example, have two calls to get the current system time. One is the call that is used to return in the packet that we mentioned, the SMB packet, the current system time to the attacker, and inside the get encryption call, they have another function. But because of the resolution of the timer, and because this is a multi-threaded, we think, server, the value returned by those calls is the same. So that's why they are leaking the time. It also has to do with the way the Maglajna system works, and a lot of things that we can talk about it in the hallway if you want, but it is possible that you can also, since we can predict and we can set the internal state of the PRNG to whatever state we want, we can practically force any machine to return the challenge that we want. So, okay. So basically, how much time do we have? 8 minutes? Okay, that's fine. So basically, in summary, like I said, what we found is, I think it's a big deal. I mean, from a technical standpoint, at least, I don't care about the hype or anything like that. When we found that, it was like, I can't believe this is happening, because it was like, I said the one thing that it should not be failing in the protocol, and it was failing. And that to us was very interesting. And from all the attacks that we showed, the passive replay attack and the active replay attack, although I think they are very efficient, because you saw that to exploit the attack, it took us, I don't know, seconds, not even a minute, you can actually improve that more. For example, instead of gathering 8,000 challenges, you can gather less challenges. You can also combine the prediction of challenges and only gather one challenge. You can do a lot of things if you put the time into actually making the attack better. We didn't do it first because we have a limited amount of time to spend on this, and then because we think that the attack that we have is efficient enough. About the prediction attack, like I said, basically what I was going to say here is what I said to him, is all the things about the fact that the server is leaking the current system time, and that current system time is used by the PRNG to generate the seed. Also the fact that the seed actually is only 2 bytes long, and then it's kind of expanded to 4 bytes, but in reality the entropy is only 2 bytes. That is also a bad thing, and all those things, and also the use of the Maglajna-Marsaglia system that can be questioned, because it's not like something you would use to do that. Perhaps that is because that code was written in '93.
Imagine as an improved LCG. So
right.
It's from
LCGs
context.
are known to be not suited for cryptographic purposes. So the fact that the Maglajna-Marsaglia system is using an LCG is something weird that you better not use it. I mean, we actually bought the paper that was explaining how the Maglajna-Marsaglia system worked, and it was written in a yes. But
they are also proposing using a table of random numbers. So
yeah, but the paper that explains the algorithm is written in a typewriter, and it says that one of the pros of the algorithm is that it uses like only one card or tape or something like that. So it was like breathing when they have like big machines and kind of weird media to store data. So it's not one of the well-known things that you would use to actually generate pseudo-random number for cryptographic purposes. The other thing that we wanted to say is that it leads to remote code execution. If Microsoft accepts that with SMB relay or SMB credential reflection, you have to accept that in this case. Like I said, one thing to remember that is something that is well known or that is known inside the security community is that a PRNG is not the same thing as a cryptographically secure PRNG. For example, like I said, LCGs are not supposed to be used in cryptography. They are only supposed to be used for statistical purposes. And the other thing is that since this is a flow that has been in the code for so long, I mean, I think that perhaps when you are, things that you have to, I think, keep in mind when you are reviewing such code that is generating random or pseudo-random numbers or that are implementing protocols similar to this one, is that if you are auditing the code and you see a call to blah, 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 random, blah, 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 don't expect that function to return the kind of random that you need. You actually have to go into the function and analyze what the function is doing. Don't ever assume that because they are calling random, even if it is a function provided by the operating system, because RTL random actually is exported by ADBA API 32, I think, I don't remember, I might be wrong, but it is exported as an API that a user can use, and it's also used in the kernel for some other things that have nothing to do with cryptography, but take care of, I mean, look for that, be careful with that. And the other thing also, that I kind of said when I answered his question, is verify how the entropy is gathered. In this case, the entropy was gathered using the current system time and adding a global variable. And that's not a good way to do it. I can't explain how to do it because it's very long to explain that. But go get a book about cryptography and read about that. And also, it's very important how the seed is created and how it's used. For example, like I said, it's not good to take 2 bytes and then expand those 2 bytes to 4 bytes because you actually do not have 4 bytes of entropy. You actually have only 2. So that might be a wrong use of a seed. And finally, you have to look for what is called side channel attacks. Side channel attack is basically, in this case, is that the server is giving us the current system that is using as the seed or to generate the seed. That is called a side channel attack because the server is leaking some information to the attacker that the attacker can use to guess or set the internal state of the PRNG. So you also have to look for those things when assessing or auditing this kind of code. And that's basically it. So if you have any more questions? No, that's it? Yes.
After the patch was released, have you effectively checked how it works against your patch?
How it works now?
No, just asking after the patch was released.
How it works what?
Did you check the patch?
Ah, yes. No comment, I don't know. No, I'm kidding. No, we just check it briefly. It appears to be, I don't know. No, it's different. We don't know. It appears to be doing something much better. That all the tests that we did, the patch passed those tests, so it appears to be okay. But I mean, as a security consultant, I don't want to say that it's okay because I haven't analyzed it. But it appears to be doing its job correctly. But we haven't spent too much time looking at it, so I don't have like a final answer about that. That's it? Right. Thank you very much for your time. Bye-bye.